Okay, good morning. Now that you all are fresh from the tea and cookies, let's get started with the third session. My name is Prasanna Deshpande. I work for MathWorks. A quick raise of hands. How many of you are aware about MATLAB and Simulink? If you could raise your hands. Okay. Do you know the company MathWorks? Okay, so let us skip a few slides at the beginning. Well, I'll just set it by one slide. MATLAB and Simulink are the two products. I'll be using these names. You should not keep on wondering what this guy is talking about. So MATLAB is a base product and Simulink is another base product that we talk. There are multiple add-on tools built on top of MATLAB and Simulink. This session is not about MATLAB and Simulink, hence I just got over it. The title of my session is Architecting Software-Defined Vehicles Through Model-Based Design. Let's first get started by setting the stage on model-based design. What is model-based design? You don't have to tell, I will tell. It's not a test, right? So, model-based design, the name makes it very clear. There is no definition. I have not mugged up any definition of model-based design. It's using models for designing your systems. In this context, using models for designing your automotive systems. Now, what is the advantage of using models? There are several systems which do require complex control algorithms where you need to follow the control system design process. Using model-based design helps you to apply fundamentals of controls and design your systems much faster and much more in a reliable way. That is where model-based design came into picture for automobile systems. What is software-defined vehicles? Lata has done a great job in the last session. Let's not get into understanding what are software-defined vehicles, but for you and me, as users, what are software-defined vehicles? A vehicle or a mobile phone which has wheels, a mobile phone where I can install and remove apps or features the way I want throughout its life. Like I get updates for my Android OS, I'll keep on getting updates for my Volkswagen Virtus also. Everyone with me? That's what, just to set the stage. Okay, what is that QR code doing there? In my presentation, I'll be sharing few successes of few large and new and innovative automotive companies. You want to learn more about it, you want to read more about it, my slides will have references, the hyperlinks from the web pages. Anywhere, anytime you would like to read more about them, feel free to scan. I will show this again on a few slides and at the last slide again, but feel free to scan it, feel free to get access to the presentation deck and thereby to the actual material that I will be sharing here. And anyway, Step In Forum they will share slides later with you. But what I believe is life is now. I don't think you ever look at those slides again and again. So do it, life is now, right? So let's get started with first digital transformation in the automobile industry. See, automobile industry initially started as a core mechanical industry. I'm sure you all agree with me. Somewhere in 1980s, I think General Motors came up with first electronic injection system. From then to today, we have about 70-80 functionalities in the car controlled electronically using software. What are the challenges we talk about it today? The challenges we talk about are mainly with respect to we are not able to get quick prototypes of the vehicle. Do you know, in long ago, rapid prototyping was a term being used for mechanical prototypes. Later on, we started using a term called as rapid control prototypes, which is where electronic prototype of control system started, that came into picture. And now we are again talking about challenge as a prototype. Secondly, rising cost of fixes. There are recalls. I have something gone wrong in my vehicle's ECU. I have to tell that my brake lever there is some problem with my brake lever, get the car back, fix it and send it back. I cannot really fix on the go. I cannot really do on the air fixes. And thirdly, people related challenges. I'm sure a lot of you look senior, so a lot of you are able to relate with what I'm saying here. Like engineers unfamiliar with software development, and then a lot of challenges come because basically automobile engineers are domain engineers. They are not really coders. So how do we address that? So that's where that's our today's or sort of yesterday's challenges in the first digital transformation. Now the second digital transformation is all about electrification, automated driving, artificial intelligence. So point number 4, 5, 6, 7 from Lata's slide. She was talking exactly about the same thing. I'm just choosing 4, I had chosen it previously, just relating to her now, but choosing 4 challenges from her presentation. So my title is about architecting software-defined vehicles through model-based design. Before getting to software-defined vehicles, I would like to spend some time on value of model-based design for these first three trends in the industry: electrification, automated driving, and artificial intelligence. And then we'll go to software-defined vehicles. That's in general, that's the way the presentation will go. So let's study the impact of model-based design on electrification. Now, what is model-based design for electrification? Electrification in this context is electric vehicles, electric or hybrid electric vehicles, mild, strong, everything. Everything in the vehicle which is helping it to reduce the load on conventional engine is electric vehicle. Let it be mild. So what do you need for electric vehicle? A model of electric vehicle. Model-based design for electric vehicle probably starts with a model of electric vehicle, which helps you to simulate any kind of drive cycle, helps you to simulate driver, helps you to simulate the controllers, plans, and then understand the range of the vehicle, the fuel economy improvement of the hybrid electric vehicle, the performance, and things like that. Are you with me? Doing system level simulation helps you to better understand your components and better design your components. Are you with me? Classically, OEMs take responsibility of doing this so that they get better clarity about the components, and then suppliers will do detailed engineering of the components and deliver the ECUs back. Are you with me? There were some of the questions in the first half related to different suppliers working on different ECUs and different functionalities, and that is where how it will be done using software-defined vehicle. That was the challenge that was discussed. So now let's understand who has got some significant success by using model-based design for electrification. I had already revealed by showing you the slide. I'll show it again now. It's Tesla, one of the companies. Well, what is so special about Tesla is, see, Tesla have their clout now. When they started back in 2006 or 7, they were just another startup company in the US, started by a mad person. When the person added method to his madness, then he did a lot of things. That's fine. But 2008, they came up with the first electric sports car called Tesla Roadster. This was developed using model-based design big time. Till now, they are heavily using model-based design for developing a lot of different functionalities onto their car. There is, at the bottom of this slide, there is an article, a third-party interview given by Tesla people to a magazine called Car and Driver. I will quickly tell you my key takeaway or my story out of this. They improved their motor efficiency by 6 to 7% by improving their motor controller. And that resulted into 15 to 18% overall vehicle range improvement. This is a big testament. Because for us, for our companies in India, the motor supplier will have to do this, and that will give the benefit to the OEM. If the OEM is relying on a supplier for that kind of things. Nowadays, OEMs are also doing a lot of things in-house. Indian OEMs are also doing a lot of things in-house. So that's another story. But then that's one value of model-based design for an OEM. Another OEM, and we have Dr. Shankar Venugopal here. This was done by Mahindra Electric for one of their vehicles, which is right now in market for production. This is battery thermal management system of electric vehicle. What Mahindra Electric could achieve for this is, again, the video is there, and there is a lot of text. Don't bother reading the text now. Get access to slides, read the text later. Listen to me now. I'm anyway summarizing everything for you. So what was the value for Mahindra Electric? They could build electrical and thermal model of the battery. They could analyze and take a decision whether they need active thermal management system for their battery pack. The answer was yes, and then they designed for it. Everything was done using 1D electrical and 1D thermal models. See, 3D thermal analysis needs to be done. I'm not saying it need not be done, but for their timelines, for their application, they could get away by doing it in a 1D way. They have used excellent engineering creativity, and the person who has done the video, Vipin Venugopal, he speaks about it quite well in the video. So I would definitely request you to go through this. Third is from China. State of health estimation pipeline for NIO car company. Now, NIO car company wanted to build cloud-based SOH estimation algorithm. SOH is state of health estimation algorithm for their electric vehicle fleet. They had one small challenge. They did not have a fleet. What they did was they simulated a fleet. Model-based design, right? Use models. So with no existing fleet, they built synthetic data by using simulated fleet. They built the complete algorithm, deployed it onto their cloud-based infrastructure. Later, as they got their fleet, they could replace the algorithm while the infrastructure was in place. So that's the value of model-based design and efficient use of data. This is not AI, this is efficient use of data. A lot of things we misuse a lot of terms. This is data. This is not, there is no machine learning as of now. I mean, they have used it, but I have not described it for you. Read it for yourself and then you will see where they have used deep learning also. Now let's go to automated driving. Now, automated driving gets benefited big time using model-based design. At MathWorks, we do have several solutions which help you to planning, detection, localization, tracking. We do have readily available algorithms, as well as we have a lot of test infrastructure. One additional thing that I would bring to your attention is this tool called as Roadrunner. This helps you to interactively build different scenarios. You can actually build roads, different constraints like this, and test your vehicle models onto this on model and also on HIL systems. I realize I'll be talking too much, and you have realized that I do have a talking habit. I'll reduce my talking. So, who has got benefited? Renault Nissan have built radar point cloud algorithm and classification algorithm using this technique, using automated driving tools. There is a video and a set of slides. Another good benefit is SAIC, another Chinese company. They have developed vehicle-in-loop simulator for LDPS, lane departure warning system, validation of their lane departure warning system. So that was another value add for them. Now, see, they have described their architecture in a very nice manner. SpeedGoat is a real-time test system. Then hardware, which is optional. So this can be optional or this can be simulated. These are controllers. Then there is real vehicle, and then there is PC and error issues. So these are some of the system diagram. That's how they have used it. Third is Mando, another supplier. They have developed planning and control algorithm for highway lane change. Now again, a lot of text. I'll highlight a couple of things. Have a look here. Planning and control done using MATLAB. Perception and localization done using C++. And then there are several tools. Adaptive, okay. They have done model predictive control by using model predictive control toolbox. They have used, okay, I'm not able to read it. They have designed a simulator and they have used robotic system toolbox for overall implementation of their system. So ROS basically, they have used ROS, robotic operating system, for doing that. So a lot of it can be done using, in automated driving can be done using model-based design again. And the third thing, use of data and artificial intelligence in the automotive industry. I'm not calling model-based design on the title of this slide, just to bring it to your notice. But we'll talk about model-based design. See, one challenge that we have seen in the industry is, long back, like 2012, 2013, the AI cloud started. Like everything became AI. Right now it is Gen AI, we know, right? Everything can be done using Gen AI. Like that, AI thing started and everyone started talking about AI. So anything I do using AI, like we had a tool called a statistics toolbox. It had a lot of statistical tools. We had to rename it. Statistics and machine learning toolbox. If you have MATLAB, you will have statistics and machine learning toolbox today. We had neural network toolbox. Of course, we have added few functions to that. Now there is a deep learning toolbox as well. Because of that, a lot of things are around it. So the point is, that gave rise to a new breed of engineers or a new breed of scientists called data scientists. Fresh graduates who are very good in scripting, who are able to handle big data in a very expert manner by doing a lot of scripting. Now the challenge is, these engineers are able to handle data, but they cannot interpret data. They cannot analyze data. Because data analysis has to be done by a person who has gray hair, like who has a lot of experience. Then only you can derive insights, right? A new person cannot really understand what to do with the data. Then there has to be joint work to be done by the data scientist and the domain engineer. And that's where a lot of challenges come into picture. What approach we support is low code or no code. We have provided a lot of apps so that domain engineers themselves can do a lot of data analysis, data analytics, develop their own algorithms, test their own algorithms. So that means you do not have to write an algorithm from scratch, or you hardly have to write an algorithm from scratch. We do support the complete workflow from data to deployment. I'll talk about it on my next slide. And most importantly, we interoperate with several open source frameworks. There are some things which have to be done using Python. No doubt on that. So that is where we should take advantage of Python, and some things which can be done using MATLAB better, we should do it using MATLAB better. I'll tell you what are they exactly. I just want to take some time to talk about what do I mean by complete AI workflow, end-to-end AI workflow. It's basically these 4 steps. Data preparation, wherever you are accessing your data from, it's your vehicle fleet, or if it's your sensors, or if it's another simulation software. Then AI modeling, which is where you do actual data interpretation, cleaning, modeling, everything, training, of course. Then simulation and test. In the context of bigger picture, by simulation and test, we mean we are integrating the AI model with the rest of the Simulink model. And then deployment. And we support deployment on embedded devices, enterprise systems, as well as clouds and edge devices. The last step is where we have seen a lot of customers getting interested in using MATLAB. They may have some struggles using open source softwares for deployment. That is where we also interoperate with Python. MATLAB also works along with Python to get a few things from here to there. And in simulation language, we call it co-simulation. So that's about AI. Now let's have a look at who's got success there. BMW is a very interesting story. So they could use machine learning to detect oversteering in their vehicle. And actually it was a set of all domain engineers. They could use machine learning algorithms. They could collect data from their vehicle, develop machine learning algorithm, generate C code from it, and deploy it back to their ECU. They did not have to write any single line of code. Completely done by domain engineers. Second example is on Goshen. Again, they have done SOC estimation, state of charge estimation framework. And again, in the slide, you will see somewhere that complete workflow from model development to production hardware. So again, SOC estimation done using AI. It went onto their BMS algorithm because it was state of charge estimation, which is typically a part of BMS, battery management system, and then deployed onto production hardware. And third, Stellantis. Now this is Stellantis case is very interesting. Some people are saying gone are the days of engines, but not really like that. Virtualization of sensors. Believe me, I'm MathWorks. We are supporting several customers in virtualization of engine-related systems, after-treatment systems. So, for NOx estimation, virtualization, Stellantis also got very good benefits. Removing one sensor from the car, replacing it with a simulated sensor saves you a lot of cost. In fact, I can speak about it. We have recently done a project with Mahindra also on the same thing, and they have spoken in last year in our conference, NOx sensor only. We helped them develop deep learning based algorithm, and now it is deployed onto their tier 1 CCU as well. The deep learning algorithm got converted to C, now deployed onto their production ECU also. So what I'm trying to tell you, model based design does have a lot of value in the digital transformation, or in the first digital transformation of the automobile industry. This slide is to summarize. We just spoke about model-based design in electrification, automated driving, and artificial intelligence. Now let us move on to the second part, which is software-defined vehicle. I don't know if I use the term, but right now I'll use it. We were always doing software-enhanced vehicles. It has started long back. Now we are moving from software-enhanced vehicles to software-defined vehicles. And this journey is also not new. If you see some articles published back in 2009, they were talking about software-enhanced vehicles, and now we have started talking about software-defined vehicles. To me, personally, software-defined vehicles is not a reality yet. It's future. Very near future, but it's future. So, the automobile industry is now transforming. We know automobile industry is transforming, or vehicles are transforming. Like a vehicle bought 12 years back and a vehicle bought recently, there is a lot of difference in the same model of vehicle also. So vehicles are transforming big time. So are our E&E architectures. Till yesterday, we had distributed control architectures. We had every ECU for a small functionality. Today we are getting into zonal computers, which is where there is a computer in the front zone, there is a computer as in, there is a ECU in the front zone, there is a ECU in the back zone, and things like that. And very soon we are getting into the popular term, HPCs, high performance computing. So high performance computers, again, that's our tomorrow. That's what is really required. The high compute is required for the heavy needs posed by software-defined vehicles. It also requires, this is the E&E architecture. So does it require us to change the software architecture? Definitely yes. And that is where we need to really understand how modeling and design tools are evolving. And that is where the next part of the rest of my presentation I'll talk about. See, while the SDV vision needs to support both development and operation of vehicles, it needs to start at the heart of this closed loop system. Where is the heart of this closed loop system? Are you with me? The title of the slide, that's the key message on the slide. SDV vision needs to support both development and operations of the vehicle. Why operations? That's where SDV comes into picture. Vehicle productionized and delivered to the customer, that's not where it ends. In fact, that's where it starts. Then I have my aftermarket, and then I have my updates and new features, and then I will still have the competition with my competitor going on. That is where, that's why that statement is made there. Now, where is the heart of this whole system? You understand? This is the heart? Okay, sorry, it was not there. Basically, to me, and of course, to me it will be, I'm from MathWorks, so system simulation, virtual integration, code generation, that's where heart of the whole SDV system lies. Well, I will be biased, no problem, you decide it for yourself, but you can't deny, definitely one of the important parts of the system. So, let's start there, and let's answer the question, how do we align SDV development practices with model-based design? Now, what do we do with model-based design? We build models, we do a lot of simulation, and we have built a kind of ecosystem around this modeling and simulation, which helps us to deploy our simulations. Okay, what we do is we build models, we test our systems, then we use simulation for doing verification and validation of our systems, then we generate code, then we deploy it onto ECU, then we do verification and validation of the ECU. There is a big process that we follow. After that process, we get our vehicles. Now, this needs to transform for software-defined vehicle process. Fundamentals remaining the same, the models need to evolve into architectures. The simulation needs to evolve into scalable virtual integration. And the ecosystem needs to evolve to support new workflows. I think I'm doing good with time, definitely not bad. Let's go through these 3 points in one level detail. Hope you are with me. So, from models to architectures, a model would look something like this, and architecture would be much more complex than a model, right? So, one can think of architecture as being a suitable abstraction of the software system that helps in implementation. And then you can think of architecture as it's basically a sliding scale, which could be as easy as a class diagram, and it could be as complex as a very detailed architecture model, which is linked with the design models, implementation, generated code, and requirements, and everything. And whatever tooling you use for building system architecture should ideally support both the extremes. It should, at the start of the system engineering process, it should help you to do class diagrams, and later as you mature with understanding of your system, you should be able to update your system architecture model, system architecture diagram, as you go with other things. So, I will quickly show user workflow for software architecture modeling. Basically, it's one slide. Give your 100% attention. I'm sure it will add some value. And then later on, we can have some discussions. For disagreements, we'll definitely have some discussions. So, we are talking about software architecture. So, he will receive requirements from system architect and stakeholder needs. These requirements and use cases are used to build software architecture, structure and behavior of the software architecture. While doing that, we understand the characteristics in terms, for example, timing, performance, and we optimize the architecture to meet our characteristics. We also look at the architecture from multiple viewpoints. These are some of the concepts from system engineering. From multiple viewpoints, different class diagrams, different timing diagrams, and based on that, we update our software architecture. Once we have confidence on our software architecture, we'll go ahead with component implementation. That is system design in a way. Once the system design is done, we go for software validation. For software validation, we'll again go back to architecture and requirements to build the test cases. And then the component implementation models will be tested while doing software validation. In MathWorks world, these are some of the tools that we use for doing end-to-end process. That does mean we do have linking from your requirements to architecture to design two implementation, two test cases. There is bidirectional traceability, which is required for several certifications, which is required for several norms to be met. So that is where software architecture modeling can be achieved. This is very similar to the SysML based approach. Only thing lacking in the last slide was service-oriented architecture. The same tools, the same approach also supports service-oriented architecture. What changes from signal-based approach to service? Okay, let's not get into what changes from signal-based architecture to service-based architecture. I'll just keep it very simple. Traditionally, what we do is signal-based architecture. We build all the models, everything with respect to time. For supporting software-defined vehicle, we need to modularize the software so that it supports OTA and other things. We have to go for service-based architecture. Let's keep it at that level. So SOA design can be done bottoms up and top down by using the same set of tools by the same methodology. Now let's go to the second point, which is virtual integration. Basically, how do we scale up from simulation to virtual integration platform? Now, shifting left is a clear trend in the V&V industry, in the verification validation industry. And in automobile industry, we use different terms like MIL, SIL, HIL, vehicle. We have already set a rule wherever there is a lot of text. That's for your offline reading. We don't have to really get into it. But if you're not aware what is MIL, what is SIL, just go through it very quickly. The key takeaway is how much should we go to shift left? Real answer is go as far as you can. And nowadays there is a big thing. We had a good conversation yesterday with one of our customers. VECU with Simulink. I'm sure you are aware about this diagram also. This diagram is not new to most of you. By VECU we mean virtual ECU. So in this diagram we always felt that Simulink was neglected. And why Simulink was neglected is, see, if you really see, for up to level 2, you need a simulation environment which helps you to use models and code. Simulink does support that. So with Simulink in-house, you can actually support up to level 2. For rest of it, you need to collaborate with different partners who have the middleware, who have the hardware abstraction layers and codes for their hardwares. So that's about virtual ECU. And we enable this by focusing on developing Simulink as the simulation integration platform. What I mean by that is Simulink can work with multiple different tools, and there are more than one ways to work with different tools. We always had something called as course simulation interfaces. Internally, we called it S functions to work with multiple tools. Now there are standards like FMI. We are supporting FMI standards. In fact, from last year, we also started supporting FMI 3.2, which was the latest standard. And I think back then, we were the first company to start supporting FMI 3.2. So you can actually import FMI 3.0 FMUs into Simulink. Another thing is, it's not always advisable to use Simulink as integration. Bring everything to Simulink. It doesn't work in the SDB world. So we also need to give you a SDK, which helps you to containerize your C application code and provide you a connection for ready-to-run code components. So that containerization is also supported for supporting the SOA needs. And another requirement we used to get is, and this is something we were discussing yesterday, this is not Gen AI, which is basically, if I give you a set of libraries, and if I select some parts, can you build a model for me? Because we know the architecture of the model, right? Are you with me? Let's say you want to build a tractor model, you have a set of libraries. From that library, you select parts. Can MathWorks build the model for you? Because we know engine is to be connected to transmission, it is to be connected to wheels and things like that. So we have come up with that with something called as Virtual Vehicle Composer. Virtual Vehicle Composer is our way to create feature-driven model. You let us know what features you want and automatically model will be built at the background. You will get a Simulink model and you can make changes to that model the way you want. There is nothing hidden, there is nothing like there is only single truth. Single truth concept is applicable somewhere else, not here. So that's about Virtual Vehicle Composer. So what we spoke in the second section is basically about virtual ECU and virtual vehicle. So virtual validation, that's what is a big trend that Lata was also addressing. So just relating to the trend in the SDV ecosystem. Now the third one is evolving modern ecosystem. Of course, we have to support continuous integration, continuous deployment. Also, we do have, support package means on MathWorks website, there is a freely downloadable package which you can download and integrate with your system so that you are enabled for using CI/CD workflows from MathWorks. And this basically model-based design is mapped to CI workflow. This slide shows it at a very high level. Basically, same steps. It helps you to find issues early by iterating locally, and then you go ahead with the CI pipeline. So, another aspect of it when it comes to enabling cloud is, can I access MATLAB online? So yes, we do have MATLAB online and Simulink online. In fact, there are several online trainings available. We call it on-ramps. If you search MATLAB on-ramp, Simulink on-ramp, you will get access to MATLAB online, wherein you can go through that course. Anyone can go through that course. It's a 2 or 2.5 hour course where you will be able to access MATLAB online. You will be able to do hands-on. So MATLAB and Simulink are now accessible. You don't have to install MATLAB for using MATLAB anymore. So that's another aspect of it. Third and very important aspect of it is, onto the evolving cloud system, it's scaling up on the cloud. Several optimization problem statement solving requires us to simulate the model number of times, like thousands and lakhs of times. And these are all independent simulations. For example, I want to maximize range of my vehicles subject to certain constraints. Constraints could be coming from road, constraints could be coming from hardware, or any other place. I can mathematically define that problem and I can solve that problem. Essentially, solving that problem involves simulating the model with different set of inputs thousands of number of times with some optimization algorithm doing some work in the background. That is where making these simulations, running these simulations, it's possible to scale up to cloud, it's possible to scale up to enterprise systems, it's possible to make use of multi-core CPUs as well as GPUs. And this slide basically shows what is the time benefit you get, how many cores you can use in parallel at the same time. So the simulation, the problem statement, which takes 1352 simulations, takes 18 hours in series on one computer, takes 5.2 hours with a quad-core laptop, which is my laptop, takes 59 minutes, about 1 hour on an Amazon EC2 instance. So that's the time benefit you get. So to summarize this part, what we have seen is models to evolve into architectures. And what we have seen is we are supporting the complete ecosystem, right from system requirement, architecture, design, implementation, testing. There is bi-directional traceability by building system architecture model, which seems to be the need for the hour when SDVs are concerned or when SOAs are concerned, service-oriented architecture is concerned. Second point, simulation involves into scalable virtual integration. We are supporting virtual ECU, virtual vehicle. Basically, the trend here is virtualization in terms of virtual validation. For that, you need to virtualize the systems, the vehicle systems, the plant models, and the controllers, and both are possible. And this is not MATLAB Simulink. This is MATLAB Simulink and many more tools. That's the need of the hour. Thirdly, for supporting cloud-related workflows, DevOps CI/CD is important, as well as accessing data on cloud, deploying algorithms on cloud is also required, and that is all supported through this ecosystem. Now to summarize the session, at the beginning, we spoke about value of model-based design for electrification, automated driving, and artificial intelligence. We went through several customer experiences, and I'll be happy for you to go through them, because my key takeaways, I have told you, you may have different key takeaways. And then we understood how software-defined vehicle architecture can be made using model-based design by reusing our models. Signal to service is basically one way to reuse our existing models, re-architect them, and use them onto service-oriented architecture for software-defined vehicles. So thank you for your patience. Enjoy the conference. If there are any questions, we can go through the questions. Yes, can you give him the mic? Sure.
So, thank you for nice presentation. I'm hearing you since last more than 10 years.
Thank you. I hope it's a thank you.
So now, since you covered some of the very interesting topics.
It's working now, it seems.
Okay, thank you. So there are several questions I have. I would like to club it together.
Sure.
One interesting point you said, like about the human insights. Human insights. So this is synthetic sensor data preparation, if I have to say. Recently, we are using and we are working on it to generate the vehicle insights. How MathWorks solutions, because I'm the user of MathWorks solutions, and I'll tell you, I do not find any such insights, vehicle insights where I can generate, or I can come out with the synthetic sensor data. I can prepare it. So I would like to hear
Sure.
you
Yeah.
on that. That is one. And okay, you can cover, then I will ask another, because I
Okay,
have.
sure.
Okay, otherwise I will club it together now.
Yeah.
SDV, as you said that SDV, HPC, and other SOA aspects you covered, right? So in SDV, you see that SDV is not just a matter of future, it's a matter of present actually. It's there already. Number one, what level of SDV we are looking, that is the
Yeah.
question.
Agree.
Now, there is an interjection. Not just SDV, it's become AIDV.
Okay.
Okay, so not just software, AI has already entered in the market. So we are talking about where MathWorks Simulic provide those libraries which can help us to design those level of algorithms.
Okay.
That is one thing. HPC, SOA. SOA is kind of, it's again a very fantastic words, but implementing is properly is a challenge.
Yes.
And that's where I see that there are old tactics is still those libraries are there. The future complex AD platform applications challenges what we see, L3 plus challenges, that is not getting addressed by the current solutions actually. And lot many challenges we are seeing, and we are blaming to hardware, we are blaming to the process, we are blaming to this, that, but the fact is we are not able to understand and simulate it properly. And
Yes, yes.
so there are some interlink. I would like to see that how MathWorks is thinking about all these problem statement, and how are you planning to address these industrial challenges.
Sure.
Thank you.
Thanks. Three very elaborate questions. We are going to have we should talk offline as well. I'll give high level answers now. For whoever these things are important, join us for the offline discussion later. I don't know when it will happen, maybe during lunchtime, but we'll do that. First was on AI. How can you get insights from vehicle data? See, MATLAB will not give you insights. MATLAB will give you tools to be able to classify different features. There are feature classifiers. How to access data. One problem, how do you access big data? There are a lot of challenges with respect to that. I'm sure you're aware about it. How do you solve those challenges? That's one. Secondly, how do you do feature classification? How do you classify? How do you look for trends in the data? And then based on that data, you'll have to apply your insights. Once you apply insights, there can be some automation built, which will be again useful for doing more AI algorithm modeling based on that data. Let's keep it at that. Second was on SOA, challenges on SOA. That was third. I remember it, I'll just complete it. You're right, SOA is a very complex thing because it involves HPCs, deploying onto HPCs, and it's not just deploying onto HPCs, it's deploying onto different middlewares. We are sitting on top of HPCs. So any application software needs to be capable to talk to different middlewares. So our embedded code generation tools were supporting different targets, so different hardwares like TIC 2000, like NXP, like Renesas, and different this and that. Now we have started supporting different middlewares. Many middlewares are Linux based, but there are few middlewares which are not Linux based also. So we are supporting those middleware deployment also. And it's not this or that, it's this and that. There is something which is adaptive AUTOSAR, there is something which is classic AUTOSAR, and both of them need to talk to each other, and then something else will come using DDS and all. That's an ecosystem, and it is how it is going. That's how it's going to be. So we have to be ready to support. Some of the things are supported today, some of the things will be supported in future, because the ecosystem itself is evolving. I missed the second question. AI we addressed, right? AI SDV, that's right. No, so you're right. See, SDV is heavily dependent on data, right? So there are two places to close the loop. One loop which is already closed is aftermarket loop. How can I make use of data which is coming from my vehicle and get a vehicle designed for my needs? I would definitely like to see that. I am an aggressive driver, but I want good fuel economy. It's okay if my vehicle does not let me drive itself very aggressively. I want to press that pedal, let the vehicle not go, I'm happy with that. So tomorrow's SDV, I would like my car company to do that for me. Make me a safe driver. I may be a threat to the road. because I drive too aggressively. So like that. So, but that's not happening today, but that's one application which is aftermarket application. Another application is get vehicle insights and feed them back to your design process. Gone are the days when we used to develop our control systems using only physics-based equations or data that is coming from vehicle. Now we have much more access to vehicle which is in the field. So why don't we use those insights and improve our vehicle designs to start with? So all these loops are getting closed. I agree with you, SDV is not, I'll not call it AIDV, but SDV, like big part of SDV is AI or data. And I'm with you on that. A lot of infrastructure is built and being built using MathWorks tools. However, it's not just about one company. It's complete ecosystem. It's the way we discuss it internally is what role we can play in enabling OEMs and tier ones to work together in this ecosystem. And there is a limited role that we can play. Everyone has to play his role so that SDV trend becomes successful. I hope at high level this is okay. Thanks. Yes.
Working on a similar project, I'm stuck with your tool. Maybe I will discuss later offline. So my problem is we are doing automotive data discovery.
Automotive?
So, data discovery.
Okay.
So for that, my main input is AutoSAR package.
Okay.
For a given vehicle, and a model and the build. And what's happening is the focus of my work is to identify the dependency pattern between each ECU of each module so that we can model it. So when I get the values of the ECU, I can know what triggers what.
Okay.
If an ECU is going beyond the threshold, which are the other ECUs that are going to be hit?
Okay.
So there is something called debouncing model.
Yeah.
Heard of it? Debouncing.
Okay.
So when the data troubleshooting code starts spitting out DTC, before it says it is in a pending DTC, it gets into a debouncing mode.
Yeah.
In that mode is a white space where we predict when a particular car is going to have problem. Even before you get to discover it and it becomes a reactive situation.
Yeah.
So for that, I'm trying to use Simulink. I want to load the AutoSAR package and get all the dependency. It only, the most I'm able to get this seat belt, what do you call use case done, but nothing beyond that.
Okay.
So if you help me, it'll be a great initiative.
I'm sorry, you were right at the beginning. I'm getting a lot of questions. I feel like asking you several questions so that I can answer. Maybe let's take this up offline.
Sure.
Sorry about that. Yeah, I think we are done with time. Maybe one last question. I think I was very effective with this set of audience. Go ahead.
Thank you. We were discussing about VECU. So I came across OpenECU as well.
OpenECU?
OpenECU.
Okay.
So I am assuming that Simulink is already supporting OpenECU concept. So can you please shed your knowledge on OpenECU?
Okay, let me give it a try. OpenECU is not VECU. This is not, please feel free to correct me. I may not be the best person to answer everything. OpenECU is not VECU. OpenECU is a development ECU provided by a couple of or maybe more companies for OEMs or tier ones to try out for doing rapid prototyping or to try out their new functions, their features. That's for develop. That exists physically. So you basically develop models, test models, deploy it on OpenECU, and quickly take it to your vehicle or test rig and test it. My understanding of OpenECU is that. Now, is OpenECU virtualized already? I don't think so. And I don't even see the need, because virtual ECU, if I am getting, I should get it for my production ECU. That will save me some steps in my development process. Anyone would like to add anything? No, but let's, she's standing behind me. You want to answer? Okay, maybe let's take that offline again. Sorry.
Can we take it in the break time?
Yeah, okay, I'm sorry.